Percentages are useful because they allow us to compare part-whole relationships. So let's take a look at a couple of examples looking at the relationship of a part to a whole. So suppose you receive quiz scores of 8 out of 10, 13 out of 15, and 22.5 out of 26. So in which quiz did you score the best? Well, for each one of these quizzes, the numerator is how many points you earned, and the denominator was how many points the quiz was available out of. Every one of these fractions, we're going to turn them into a decimal, and then from the decimal, we'll turn them into a percent, and it will allow us to do this comparison. So for the first quiz, 8 out of 10 as a decimal would be 0.8 or 80%. For the second fraction, 13 out of 15 is equal to 0.86 repeating. Moving this decimal 2 spots to the right, that would be 86.67% if I were to take it out to the nearest hundredth of a percent. For this last one, we earned 22.5 out of 26 points. Converting this to a decimal by doing 22.5 divided by 26, we get 0.8653, and so on. Converting this to a percent by moving this decimal point over 2 spots, we get that it's 86.54%, rounding to the nearest hundredth of a percent. So in which of these quizzes did we score the best? Well, it's going to be the one that has the highest percent. So this one was the one that we scored the best, just by a little bit. Now suppose Anne received a 15% tip and Cedric received a 17% tip. So two questions: who received a better tip and why? And who received more money and why? Now in terms of who received a better tip, we would argue that Cedric received a better tip. Okay, so why did he receive a better tip? Because he had a higher percentage of the bill returned to him. But on the second question, who received more money, this one we have to know then what these percents are actually being applied to. So we have to know what the bill was or what the whole was in order to actually figure out how much money each got. So who received more money? That we don't know. So why won't we know that? We need to know the whole. So for instance, let's say Anne received 15% and she received 15% on, I don't know, let's say a $100 bill. So then that means she received $15 back. Now let's say Cedric received 17% but on $1. So that means Cedric received 17 cents back. So in this case, even though Cedric got a higher percentage returned to him, Anne received more money. So here's when we're working with percents, we have to be very careful that we know what the whole this percent applies to. And that will tell us then the part that is returned to the individual. This relationship of the percent and then the whole and then the part returned can be expressed formally by this equation, which I call the percent equation. It's the part is equal to the percent, and when we work with it, we'll have to write the percent as a decimal and then times the whole. You might have seen this equation as represented as the part is equal to the rate times the base. Okay, so this percent is sometimes referred to as the rate, and then the whole is sometimes referred to as the base. Okay, so this is going to be the same idea. So let's take a look at a couple of examples applying this percent equation. Now in this first example, it says a family went to dinner at a restaurant. Their total bill was $48, and they left 15% of their bill as a tip. So how much did they leave for a tip? Well, the part that they're going to have left for the tip is equal to the percent times the whole. So the part is going to be the tip amount. The percent that they're going to leave behind is 15%, and they're going to leave behind 15% of $48. So 48 is going to be my whole. So if we go ahead and calculate that, we get that the tip then is going to be 7.2 And recognizing that the tip is money, this is not an appropriate way to talk about money. So then ultimately we would say that this is going to be $7.20. So we'll take it out to 2 decimal places, and then we should have units on our answer. Let's take a look at another scenario. So it says the bottom of your receipt says you saved $12.25 today. Now you bought a shirt during a 40% clearance sale. So how much was the shirt? So again, in this percent equation, the part is equal to the percent times the whole. You saved 40% of the cost of the shirt. 40% of the cost of the shirt equated to saving $12.25. So 40% of some number is equal to $12.25. So there's the numbers put into the equation. So I would have $12.25 equals 0.40 times x. We'll solve this for the variable by dividing both sides by 0.40. All right, doing this division, we get 30.625. So how much was the shirt? The shirt was going to be then $30.63. So we're going to round our final answers to the nearest penny. You paid $3.25 in sales tax when your subtotal was $35.14. So what's the sales tax rate? So in the percent equation, that the part is equal to the percent times the whole. The subtotal is going to be our whole, which is $35.14, and then the part I paid out with respect to that is $3.25. So 3.25 is my part. In this problem, the percent is unknown. The whole was $35.14. To solve for the variable, we'll divide both sides by 35.14. So then putting this in your calculator, you're going to get 0.09248, and that's going to be enough. All right, so moving this decimal over 2 spots then, because this is our percent, but in its decimal form. So to convert this back to percent form, we'll move the decimal over 2 spots. So this will be then 9.248 blah blah blah, and now I can throw a percent sign on there. And then sales tax rate, we'll round this to the nearest hundredth of a percent. So hundredth would be 2 spots out. So since this number is 5 or bigger, I'm going to round that number up. So this would be 9.25 and then percent. So notice on this one, we're expressing our answer as a percent. And what the directions would look like is maybe we would say rounded to the nearest hundredth. All right, so then when you do this rounding, you don't do the rounding when it's in its decimal form. Okay, so you would convert from the decimal form to its percent form, and then now that you have it in its percent form, then in this here you would round to the nearest hundredth. All right, one final application of using this percent equation, and this one is going to take a moment to kind of wrap our head around what's going on here. So it says a used car is sold at $2,400 less than it costs new. Now if it's sold at 75% of the cost of a new car, what was the cost of the car when it was new? Now in this problem we could take 2 different approaches depending on the relationships that we're seeing in these numbers. Now this $2,400, this is how much money you saved. So sometimes we refer to that as the discount. So this $2,400, how much is you saved? But over here it told you that the car sold at 75% of the cost of a new car. Well, if it's selling at 75% of the new car cost, that is equivalent to saying that you got 25% off the new car cost. So 75% of means you got 25% off. And when you got 25% off, that equated to a discount of $2,400. Okay, so this $2,400 relates to the savings, which relates to this percent in terms of the discount. So this is one way we could set this problem up. So we could say then, okay, so that the part is equal to the percent times the whole. The part that we saved, our discount, was $2,400. Okay, this is really equivalent to like this problem. This is the part we saved. Now in this one, we don't know what the percent discount was. We don't know what the percent we got off. Oh, sorry, we do. We know the percent we got off. It's 25%. And it's going to be 25% off of whatever that original price was. So this is one way we could set up this problem. The $2,400 savings equates to 25% of some sort of number. So then to solve for the variable, we could divide both sides by 0.25. So then when we do this division, we'll get that $9,600 is equal to X. So this is the cost of the new car. Now this is one way to set this problem up. Another way to set this example up is to recognize that the final price of the car is going to be 75% of the original price of the car. And the final price of the car, if the original price is equal to X, then this sale price, or maybe we'll call it the used car price, is going to be $2,400 less than that, or X minus 2,400. So then I can use these two in the percent equation. Okay, so the part is equal to the percent times the whole. Okay, so 75% of the original price is going to be equal to this used car price, which is going to be the original price minus 2,400. And then I could solve this equation instead. So then kind of maybe cleaning up what I have here, I have X minus 2,400 is equal to 0.75X. And so solving this equation, we want to get our variable terms together, so I'm going to subtract this to move it over here and join this variable term. So I would get negative 2,400 is equal to, doing the subtraction, as a reminder there's a 1 that sits right here, so I would have 0.75 minus 1, or a negative 0.25, and then the variable X. And then dividing both sides by negative 0.25, we get that the variable X is equal to 9,600. Okay, so this is two different approaches to the same problem. If I want to use this 75% directly, this 75% will relate the original price to the used car price. And I know the used car price is $2,400 less than the original price. So that's being reflected by this equation. Another way we could approach this problem is we can appreciate if we were going to pay 75% of the cost of the new car, that equates to then having a 25% discount, or 25% off. So 25% off means I saved $2,400. That sets up this equation over here. So notice we actually would end up with the same value.